Hello and welcome. We are discussing gravimetric analysis in this portion of lecture. Gravimetry is a method of analysis by the measurement of mass. As the definition of gravimetry goes, it's the isolation of an element or its compound of definite composition and measurement of mass or weight, generally by precipitation, is called gravimetric analysis or simply gravimetry as we put it. Apart from this, other methods which include estimation of ions are electrogravimetry, chromatographic separation, and so on. These are some of the common laboratory equipments we use for gravimetric analysis of metal ions in a particular solution. And as already mentioned, gravimetric analysis is the precipitation of ions in solution. So, for precipitation we need various apparatus as is given or shown in the figure, which are the conical flask, the china dish, and a funnel for filtering out the precipitates, the weight box, the burette for putting out the solutions, and so on. Whenever we discuss about gravimetry and the analysis of a particular metal ion by gravimetric analysis or by the formation of a precipitate of the ion, there are certain qualities which need to be possessed by the precipitate. The precipitates in gravimetry should be highly insoluble, that is, they should not go into the solution since they have to be weighed, and if in case they go into the solution, then it may cause error in gravimetric analysis. The precipitate should be easily filterable and washable, that is, the filterable portion where the precipitates need to be filtered either through a filter paper, which is a special filter paper used for gravimetry, and not the normal filter paper which we use in daily works in the laboratory. These precipitates should be washable, that is, they can be washed and should not be soluble in the water solution, and should possess a definite composition. That means they should not change their composition upon heating, or they should be changeable into a compound having a definite composition so that they can be weighed easily. And this conversion of a precipitate into a compound having a definite composition is achieved by the ignition of the precipitate. So, what is the difference between ignition and drying is what we need to know after this. Ignition of the precipitate is the strong heating of the precipitate to drive out all the water of crystallization or even the water of constitution apart from the adhering moisture. Drying of a precipitate is the heating of a precipitate to drive out simply the moisture which is adhering to the precipitate. Adhering means adsorbed, it's a surface phenomena. And this can be achieved by drying the precipitates in the oven at a particular temperature which is specific for each particular metal ion. When we talk about the precipitating agent or precipitant as we say, is the reagent which is added to the metal ion solution to produce the precipitate of the metal ion solution. Always an excess of the precipitating agent or the precipitant needs to be added in gravimetry to form the precipitate, because small amounts of a common ion help in the precipitation by shifting the equilibrium towards the unionized salt. However, a large excess should be avoided because it will change the ionic strength of the solution and thus the activity coefficients, thereby increasing the solubility of the precipitate. So, when we talk about a precipitating agent, it needs to be added in excess so that the metal ions form a precipitate quickly, because the addition of the precipitating agent will shift the equilibrium towards the left side and A large excess needs to be avoided, because if a large excess of the precipitating agent is added, then it may change the strength, ionic strength of the solution, and it might result in the solubility. After that, once the precipitate has been formed, this needs to be filtered. The filtering medium which can be used, like Whatman 40 filter paper or filter discs. Whatman 40 filter paper is a filter paper which is having a very small pore size, which does not allow the precipitates to pass through it. The precipitates of any particular metal ion which are produced are very small in size, of the order of micrometers. So we need a filter paper which will not allow the precipitates to pass through it, and those precipitates should be able to collect on the filter paper. The normal filter paper which we use in the laboratory for day-to-day experiments has a large pore size, and these metal ion precipitates can pass through it. Another filtering medium which can be used is the filter disc, which is present in the sintered glass crucible, which can retain particles up to 10 micrometers. The molecular size of a precipitate generally is 0.1 nanometers, so they will not pass through the filtering medium. However, colloidal particles have a size range 0.1 micrometers to 1 micrometers, so they can pass through the filtering medium. So we have to take care that whenever we are producing a precipitate with the help of a precipitating agent, that precipitate should be in form of size which is 0.1 nanometers and should not be in colloidal form. It should be in a clear precipitate form. Colloidal form will result in the passing of that particular precipitate, which is very small in size, through the filtering medium. So once we have discussed about what is that the solution of a colloid, the precipitate should not be in colloidal form, we need to first know what are the properties of colloids and why they should be avoided in gravimetry. So colloids have the following properties. Number one, they show the Tyndall effect, which is the scattering of light. They also carry charge, that is, they show movement under potential gradient. They have a very large surface area, that is, surface area per unit mass is very high. They can be separated from the true solution by dialysis. So these are the properties of colloids which make their size very small. Colloidal particles are very small in size and hence can pass through the filtering medium. There are two types of colloids which we know, which are lyophobic colloids and lyophilic colloids, and both these colloids have their certain properties, and how they are different we need to know. Lyophobic colloids are also called sol. Lyophilic colloids are also called gels. So as we know, the gels or the gelatin which we use in maybe in creams or certain face gels, they are all lyophilic colloids. Lyophobic colloids cannot be set. For example, metal sulfides and metals in finely divided form. However, lyophilic colloids can be set into a jelly-like mass. For example, gelatin or silicic acid. Lyophobic colloids can flocculate or coagulate with small concentration of the electrolyte. Flocculation or coagulation is the conversion of a colloid into a precipitate. So, lyophobic colloids can convert easily into a precipitate with even small concentrations of electrolytes. Lyophobic colloids have very small surface area, and on addition of the electrolyte they can easily precipitate out. Lyophilic colloids need large concentrations of electrolytes for flocculation. So, since small concentrations of electrolyte are needed to coagulate the colloids so that the precipitates come out from the colloidal to the molecular form, a little bit of acid is added to the solution of the metal ion to be estimated gravimetrically. So when a solution of a metal ion is taken and in that the metal ion needs to be precipitated out, in the form of according to the precipitating agent which has been added, then before the addition of the precipitating agent, a small amount of acid is also added. That acid behaves as an electrolyte and converts any colloidal form of the precipitate into the coagulated form. Peptization is an error which is associated with gravimetry. It is the dispersion of a flocculated solid to give a sol. That is, what we require in gravimetry is a precipitate which can be filtered out. However, the reverse, that is the conversion of a precipitate into a colloid or a sol, as we have just said, sol is a lyophobic colloid. So, the dispersion of a flocculated solid or a precipitate to give a lyophobic colloid is called peptization, and therefore it is the reverse of coagulation. Peptization is a source of error in gravimetry. If it occurs at any stage during precipitation, it may lead to the loss of the precipitate. Since colloids contain a fewer number of particles, the electrical conductivity of colloids is less than that of ionic solutions. So, since peptization is a source of error in gravimetry, there is a need for the prevention of peptization. For that, a small amount of gelatin is added to gold paint. Gold paint is actually gold sol in a solvent, which is a lyophobic colloid, to prevent coagulation by forming a protective colloid. So, as we know, gelatin is lyophilic colloid, as we have just seen in the difference between lyophobic and lyophilic colloid, and gold paint is a lyophobic colloid. So, gelatin is added to gold paint so that it is able to form a protective colloid. It forms a layer, or as we say, a lyophilic colloid forms a layer on the lyophobic colloid. This is because lyophilic colloids are difficult to coagulate, and if added to lyophobic colloidal solution, they prevent the coagulation of the latter also. In gravimetric analysis, peptization needs to be prevented, and this is done by adding an electrolyte. The minimum amount of electrolyte required to cause coagulation of a precipitate is called flocculation or coagulation value. That means, if a precipitate is present in the colloidal form, then the minimum amount of electrolyte which needs to be added to convert that colloidal form of a precipitate into the actual precipitate is called coagulation value of the electrolyte. To prevent the concentration of the electrolyte to fall below the coagulation value, the wash solutions used are not simply water but dilute solutions of electrolytes. That is, once a precipitate has been formed and it needs to be analyzed, then after the formation of the precipitate, that precipitate needs to be first washed before filtering it. For washing a precipitate, wash solutions are needed, and wash solutions are simply not water but a very dilute solution of the electrolyte. This is because if we are washing the precipitate simply with water, then the concentration of the electrolyte which is already present in the precipitate might fall below the coagulation value, and it might result the passing of the precipitate into colloidal form. So, to prevent that, the wash solutions used are the dilute solutions of electrolytes. That means a very small quantity, say 1 ml of an electrolyte is added to 100 ml of water to wash the precipitate. There are certain other sources of error in gravimetry which result in the loss of precipitate. Another source of error we are discussing now is supersaturation. Before discussion of supersaturation, we need to know what is solubility. Solubility is the amount of a substance a known weight of a solvent can hold when the solute and solvent are in equilibrium. That means both the solute and the solvent in equilibrium or in equal amounts, and that at that particular stage the amount of solute present is called as the solubility of that particular solute in the solvent. In relation to solubility, now we have supersaturation. Supersaturation occurs when a solution holds a greater amount of solute per unit volume corresponding to its weight. Supersaturation is a metastable state. In concentrated solutions, the particle size is smaller, leading to supersaturation and hence loss of the precipitate. Higher the initial speed of precipitation, smaller is the size of the precipitate. To reduce the speed of the precipitation and thus increase the size of the precipitate, solubility needs to be increased. So what we have concluded from this slide is that supersaturation is a metastable state, so it can easily be avoided. Metastable in the sense it does not remain for a long time and it needs to be avoided. In concentrated solutions, as we have just discussed, the particle size is very small, because in concentrated solutions the number of particles are more, and if the number of particles are more in any concentrated solution for that matter, then these particles will be very close to each other, leaving less amount of interstitial spaces. If the particle size is small, then that particle might pass through the filtering medium and hence it will result in the loss of the precipitate. If the initial speed of precipitation is high, that is, the moment you add the precipitating agent, the precipitates start forming quickly, then the size of the precipitate will be small, because the formation of the precipitate initially will be having small granules, and if near that small granule again a very small granule comes of the precipitate or a particle, then implying the initial speed of precipitation being high, then there will be no space for the initial granule or initial particle to expand. So the sizes of all the particles which are there in the precipitate will be very small, and if the size of the precipitate is small or if the size of the particles is small, then again it will pass through the filtering medium. So for that, the speed of the precipitation needs to be reduced. By decreasing the speed of the precipitation, the size of the precipitate increases, and for this the solubility needs to be increased. More the solubility of a precipitate at a higher temperature, more faster is the precipitation in cold solutions. That is, if a precipitate is soluble in hot solution, it will form a very good large particle size precipitate in cold solutions. The solubility of a precipitate therefore needs to be increased in hot solutions, and it can be increased by increasing the temperature of the solution. Hence, hot solutions are recommended in gravimetry. So, whenever gravimetric analysis needs to be carried out, or whenever precipitation needs to be carried out in gravimetry, it needs to be carried out in hot solutions. The medium of precipitation can be adjusted so that the solubility of the precipitate is more. Since supersaturation is a source of error in gravimetry, therefore it needs to be reduced. However, it cannot be totally avoided. Supersaturation can be reduced by using dilute solutions, wherein small particles act as nuclei for the further deposition of particles, leading to the formation of bigger particles. This point we have already discussed, that if we need to have bigger particles so that they are retained on the filtering medium, then in that case dilute solutions are needed. Dilute solutions means lesser amount of particles, and in that case if the amount of particles are less, then the size of the particles will be more, since one particle which is formed will act as a nuclei for the deposition of another particle, and so on and so forth, which leads to the formation of bigger particles which are easily retained on the filtering medium. The second way in which supersaturation can be reduced is by using hot solutions. Hot solutions reduce supersaturation in many ways. First of all, they increase the solubility of the precipitate, and this is required. The increasing of solubility is required, as we have already discussed in our previous slides. As we can see in this figure, the small precipitates or particles are acting as nuclei for the formation of bigger particles. The constant change helps to disturb the metastable state of equilibrium. Once we talk about a hot solution, as we have just said, they reduce supersaturation by increasing solubility. Hot solutions also decrease supersaturation or reduce this error in gravimetry by constantly changing. That means the particles which are touching the surface of the bottom surface of the container, they are getting hot, then they are moving up because they become lighter. The heavier particles are moving down, hence causing a constant change in the solution which disturbs the metastable state of equilibrium. The constant stirring also helps to disturb the metastable state of equilibrium. Once a solution is being heated, it needs to be constantly stirred with the help of a glass rod. By the solution we mean the metal ion solution, in which the precipitation needs to be carried out. Then the addition of the precipitating agent should be very slow, and this is again to increase the particle size. The adjustment of alkalinity or acidity of the medium needs to be done to increase the solubility of the precipitate. Thank you.